All right, guys, we'll go ahead and get started. So this next bit, the next hour or so, Rizwan Qureshi is going to go over the Mars B-plane tutorial, Mars B-plane targeting tutorial. So folks on the phone, you'll want to open your user guide and go to
page 75. Just give me a second.
Page 84 in the PDF.
Yeah, 84.
And we'll start from there. So Rizwan is a GMAT team member, and he's been working with JWST, and he's actually the person in charge of the graphics and reporting and plotting and 3D visualizations and whatnot. So I'll leave it from there, and he's going to take over till about 3 and introduce Steve Cooley for our next tutorial, and we'll take it from there.
Okay.
You need anything?
No, I think it's pretty set.
We got cookies in the back. I don't know if
oh, that's right. Yeah. We got
cookies now. Yeah.
We got cookies from Subway. There are about 24 of them. So I think even if you guys eat 2 each, it should be sufficient.
We had let's see. There was a break scheduled, right?
After
the 2, so after Cooley's 2:45. Yeah.
Break. Okay.
All right.
Okay, so once again, everybody, my name is Rizwan Qureshi. I'll be going over this Mars B-plane targeting tutorial. So this sketch pretty much summarizes what we're going to do in GMAT. It's a mission to Mars using B-plane. So the first phase will be Earth's departure phase, in which we already have a state from for an outgoing hyperbola, departure hyperbola. We already have a hyperbolic state. And then the second phase is heliocentric transfer phase, in which you come out of Earth's sphere of influence, and then you go to this transfer arc in heliocentric transfer phase, in which the primary governing body for dynamics will be sun, gravity from sun, and then you'll propagate to around 15 days after leaving Earth's SOI. And you'll do one maneuver called TCM, trajectory correction maneuver. And the purpose of this maneuver is to target coordinates on the B-plane, which is going to be attached to Mars. So you'll vary TCM, trajectory correction maneuver, 3 components of this delta V1 vector, and you'll target 2 components on this fictitious 2-dimensional B-plane, which is attached to Mars. And then once you get close to Mars, so the purpose of B-plane targeting is to get you close to the targeting body, which in this case is Mars. And then once you get close to Mars, we'll be on an incoming arrival hyperbola. Let me see if I can draw that. Yep. And then we'll stop at we'll give it a stopping condition of stopping at Mars periapsis. And once you're at Mars periapsis, we'll do this second burn called Mars orbit insertion, delta V2. And then you'll do this burn to slow down the incoming hyperbola and capture about Mars. So it's going to be a 2 targeting routine in GMAT. First targeter will target B-plane components to get close to Mars, and then once we're close to Mars at Mars periapsis, we'll come into the second targeter, in which we'll perform MOI, Mars orbit insertion, and then capture about Mars, and we'll orbit around Mars for about 1 day or so. So this is pretty much a summary of what we're gonna do. So in the user's guide on page 84, we have Mars B-plane targeting tutorial. I'll just explain to you what the B-plane looks like. So as I mentioned again, so this is a fictitious 2-dimensional plane that is attached to a central body. In this case, it's Mars, and then we'll be targeting 2 components, B.T and B.R, during the first targeter. And then our constraints are that we have to make B.T to be 0, and B.R will be minus 7,000 kilometers. So the asymptote of the incoming hyperbola will be piercing around at this place on the Mars B-plane And the reason for that is that we want to give the inclination of the incoming hyperbola to be around 90 degrees with respect to Mars inertial.
So, this is for the solar rays to keep the sun angle in your solar rays or something?
I'm sorry?
You're trying to constrain to make sure you have positive power on solar rays or something like that?
No. This is actually just a constraining that your inclination of the incoming hyperbola around Mars is 90 degrees, and once you do
Or it just gets you into the right orbit.
exactly, yeah. So that you have an inclination of 90. Yep, yeah. So at this point, let me start GMAT. So what we'll do is we'll just click on this new mission button. It's going to take us to the default GMAT configuration. Just press OK or yes. And in the scripts folder in the resources tree, just right click on it and add script. And go into GMAT fundamentals folder and click on tutorials and select tutorial Mars B-plane targeting starting. Not the final, but the starting. And I'll explain to you why we're doing this. So once you have the tutorial uploaded, click on it and click on Save Sync. And what Save Sync will do is that all the resources and commands that are in the script, it's going to migrate them into GMAT's resources tree and also in the mission tree. So I'll hit Save Sync. And the reason why we're doing this is I'm implementing half of the script which is in resources tree. I'm implementing all the resources that we needed to create.
How did you get into that window?
Into the
scripting window for what? I'm trying to figure out.
Sure, okay. Let me zoom in. You see this this scripts folder in the resources tree?
That would do it.
Okay.
Which one?
So just right click on it.
Right.
On the scripts.
Got it. Now I see.
Yep. And just go to GMAT fundamentals. And you'll see a tutorial called in the tutorials folder you'll see tutorial Mars B-plane targeting starting. Just double click on it. And once you have it in GMAT, just open it up and hit Save Sync. So the reason why we did this is because if we wanted to create all the resources in GMAT for this tutorial, it's going to take such a long while, probably two hours. So what we did is that we just ran the first half of the script in which it populates all the resources that we need to run this mission in the resources tree. And what we're going to do actually for this tutorial is actually in the mission tree, we'll populate all the commands and we'll go over how to create two targeters to achieve our to complete our tutorial. So I'll go over briefly all these resources that we created. And again, once again, we named the spacecraft Maven because this tutorial is actually simulating a mission to Mars, which was Maven spacecraft, which was launched a couple of years back. So the flight dynamics team gave us the parameters for that mission, and we just converted that into a tutorial in GMAT. So Maven spacecraft is shown here. I'll just open it up. So as I mentioned before, that we have already the initial epic for the outgoing hyperbola. So we have the initial state, which is the outgoing hyperbola, minus 32,593 SMA, eccentricity of 1.2, 28.2 inclination, RAN of 173, AOP of 240, and to anomaly of almost 360. And we have created a main tank. It's going to be used while we're doing burns so that we can calculate how much fuel we expended for each burn. And the parameters for this main tank are pretty much the default, except changing the 1,718 kilograms of fuel. And all the rest of the parameters are just the default GMAT parameters, like fuel density and temperature. So within the Maven spacecraft, if you zoom into ballistic mass, into tanks, you'll see that we've already selected the main tank which we created. That we've attached this main tank to the spacecraft essentially. And we also created two burns, trajectory correction maneuver, TCM and MOI. So local coordinate system is local, Earth, axes are VNB, velocity, normal, binormal. And we've selected the option of decrement mass from the fuel tank, which is the main tank that we created. Now for the gravity, we've created 3 propagators that will govern the trajectory in each regime. Well, first, which is departing from Earth and propagating up until Earth's sphere of influence. And the dynamics for that will be governed by near Earth propagator.
Question.
Uh-huh.
So it seems like you create the name, like the variable for maintain sort of before you create what a maintain is. Is that right?
No, actually, we created a resource main tank within the script language.
Yeah, but so you have GMAT maven.change equals, and then it seems like there you assign name main tank, right? And then later when you create.
Yeah, essentially, you're right. So per se, well, actually, this field will not be there in the beginning because it's empty. But when you first create main tank, then you wanna come into resource in the default spacecraft or in the spacecraft resource. Then you'll actually select main tank for that particular field. Otherwise, by default, whenever you create a default spacecraft, this field is actually not even shown in the script mode.
Yeah, but I'm talking about if I wrote this script from scratch, I could write that.
Oh yeah.
Before I created the main tank.
Oh yeah, absolutely. And then you could just write that and then go back in the and then create the main tank resource. But you'll have to be sure that the main name is obviously the same. And so when we're actually close to Earth, the propagator that we'll use is near Earth. Let me just open that up. So we'll use Runkata integrator, Runkata 89, RK89, and central body will be Earth. Primary body is Earth, and we're using gravity model of JGM2, non-spherical gravity, degree and order of 8×8, and the point masses are Luna and Sun. And we're just decided to turn on the solar radiation pressure for this particular propagator. And SRP model is spherical. And deep space, once you're in the heliocentric transfer regime, the dynamics will be governed primarily by Sun's gravity. So we've created central body to be Sun, and we've just selected point masses pretty much all the major central bodies in our solar system: Earth, Jupiter, Mars, Saturn, Uranus, Venus. And again, we've selected for the SRP to be on. And we're using PD78 this time. The reason we're using PD78 for this heliocentric regime is because it's like around 280 days of propagation. And we found out that for such long propagations, PD78 is usually the fastest as far as performance goes and runtime goes. And once we're at close to Mars, then Mars gravity takes over the trajectory. And we've created near Mars propagator. The central and primary body are Mars. And we're using Mars 50C gravity, non-spherical gravity model, degree and order at 8×8. And point mass is Sun. And we've again turned on the solar radiation pressure. This I talked about. And differential corrector that we'll use during our targeting is just a default to DC that we have. This max iteration of 25. So 3 views that will govern 3 phases of the mission are Earth view. So you'll see an outgoing departure hyperbola, and we've configured it slightly. We selected the coordinate system of Earth, mean J2000 equatorial. Spacecraft is Maven, central body is Earth, and viewpoint vector where the camera is located. And we're looking towards Earth essentially. And solar system view will be the heliocentric transfer phase. Again, we've selected Maven spacecraft and the celestial bodies, objects that will be drawn Earth's orbit will be drawn around Sun, Mars orbit will be drawn around Sun, and you'll see Sun also, and you'll see also Maven spacecraft in that transfer phase going towards Mars. And in this case, we've selected coordinate system to be Sun ecliptic. So viewpoint reference Sun vector. The camera location is located at I believe this is 50,000 or 5 million, I believe. And again, the view up direction is Sun ecliptic. And similar story goes with Mars view. When we're close to Mars, we'll see an incoming hyperbola, and it will stop towards Mars periapsis, and then you'll see a capture orbit around Mars. Mars and Earth are selected as celestial bodies. Mars inertial is the coordinate system that we selected, and viewpoint vector is located at 22,000 and 22,000 x, y, and 0 in z direction, and it's looking towards Mars in the view direction. Okay, so for this tutorial, we created 2 coordinate systems essentially. We created Sun ecliptic. By default, Earth mean J2000 equatorial and Earth MJ2000 ecliptic are created already in default, in GMAT. So Sun ecliptic we had to create for this tutorial, in which the origin is the Sun type, axis type is the mean J2000 ecliptic, and we created Mars inertial, whose origin is again Mars, and axis type is body inertial. And if you actually look at the script, you'll see that we've created Maven spacecraft, we've created a fuel tank, we've created near Earth force model propagators, and essentially every resource that I went over in the resources tree in the GUI mode, we've created with all these script snippets. TCM trajectory correction maneuver, impulsive burn, and MOI Mars orbit insertion, and the 3 orbit view graphics windows. You'll notice that in the script I've commented out everything after begin mission sequence, and so this is actually the heart of the tutorial that will actually implement all these segments. So within the tutorial, let me just minimize GMAT. Essentially from page 84 all the way up to page 82, we've essentially done all these steps by running the script. Otherwise, if you were taking this tutorial, let's say in your office, you will actually create all the resources within the actual tutorial. But to make this tutorial really go fast, we just already populated all the resources. So the real tutorial essentially begins on page 91, and then let me just jump onto there. So page 83 of the tutorial, I'll just zoom into the first targeting sequence. So as I was mentioning before, that we'll essentially prop to 3 days, and then we'll reach the end of Earth's SOI, and we'll prop another 12 days to reach TCM, the epoch of TCM, and then we'll vary the 3 components of the TCM, which are velocity, normal, and binormal directions of the delta V vector, and then we'll prop for another 280 days, and we'll prop to Mars periapsis, and then our 2 constraints are B.T and B.R. And then this will actually help us get close to Mars periapsis. Okay, I think you guys should skip these first three directions here, instructions here, because we're not gonna delete propagate 1 because it's already been deleted for you. So we'll just start from point number 4. So I'll just go over the instructions as you guys walk through it in your GMAT.
Page 83, step 4 is what we start.
Yeah. So what you'll see is right click on, go to mission tab, right click on mission sequence, and click append, and click on target. And you'll see that target 1 and target 1 are inserted. And then you click on target 1 to rename. You rename that to target B, target desired B plane coordinates. You right click and you essentially append all the commands. You append propagate. You rename this propagate to prop 3 days. So first we're actually renaming inserting all the commands, and then we'll actually go into the individual commands and we'll actually set them up according to what we want them to do. Prop 3 days, and then you append another propagate command. Right click, click rename. Prop 12 days to TCM. You right click on the first targeter, append vary. Name that to vary TCM dot V. You vary TCM dot N. And then rename the last vary command to vary TCM VNB. And we insert in the maneuver. We still have to apply the maneuver. Rename that maneuver to apply TCM. And append another propagate command. You prop 280 days. Append another propagate command, prop to Mars periapsis. Now we insert in the achieve command, achieve b.t, and insert in another constraint. Rename that to achieve b.r. So at this point everyone should have this first targeter sequence in GMAT. Let me just make sure. Prop 3 days, prop 12 days with TCM, vary TCM.v, vary TCM.n, vary TCM dot apply TCM, prop 280 days, prop to Mars periapsis, 2 constraints, b.t, b.r. So essentially in the first targeting sequence, these are our controls that will vary, 3 controls, and these are our 2 constraints that we want to achieve. So this first targeter is essentially 3x2 targeting scheme, in which you're varying 3 variables and you want to achieve 2 constraints, b.t and b.r. Is everyone at this point? All right, so I'll go in each command now. and we'll manipulate them, okay? So at this point, I'm on page 85. Let me just, I'm sorry, the numbering is a bit different on my, we'll minimize this guy. Yeah, I'm on page 94 essentially, but on here it says 84. So I'm on page figure 49, okay? Within the tutorial. So it says that we should just open up target desired B-plane coordinate system, and we should change the exit mode to be save and continue. So what this mode does is that during each iteration in the targeted sequence, it's gonna grab the first solution, and it's gonna use that as the initial guess during the second run. So it builds up on each solution that you get, initial perturbed solution that you get during each run in the targeting sequence. So we hit save, select save and sync, hit apply or OK. Now you double click on prop 3 days, and you'll notice that by default near Earth is selected as propagator, which is good because we're still inside Earth's sphere of influence, so we want the governing dynamics to be coming from Earth. And spacecraft is Maven. In elapsed days, now we'll vary this guy actually. We'll click on this guy right here, and then we'll actually select elapsed days instead of elapsed seconds. So I'll go to elapsed days, and I'll select that to be 3 days. Hit OK. Now I'm on figure 51. We click on prop 12 days for TCM. Now at this time the default is actually selected to be propagator near Earth, but we should select this guy to be deep space propagator, so we'll change this guy. You click on this gray box, you select deep space, click OK, and again in the parameter in the Maven elapsed seconds we'll change that to elapsed days. Elapsed days, and we'll change that to 12 days. Okay, at this point we'll vary actually the 3 components of the TCM, the first delta V vectors, 3 components. So I'll click on vary TCM.v, and we'll essentially we're at this step right here on figure 52, and you'll have to actually copy and paste these values or just type them in: initial value, perturbation, lower and upper, and max step, and OK, and just insert them into this TCM.v figure, and I'll just copy and paste them from my PDF, or I'll just type them in. TCM.v. So we'll make initial guess really small. Perturbation will make it 0.00001. Lower value will make it and max step will make it to be 002. So this is for TCM element 1, which corresponds to TCM.v vary command. And you'll notice that this is already selected to be TCM element 1, which corresponds to the velocity component of delta V vector, which is good. This is what we want. So we hit apply. Now we do the same thing with the TCM.n. But this time you'll notice that the TCM.element1 is selected, but we'll actually select TCM.element2, which corresponds to the normal component of V and B. So we click on edit. We click on, just make sure to select TCM first and click on element 2. And just double click on it, it will just bring it to TCM.element2 selected values. Click OK, and we do the same thing. We just copy and paste.
Question about that one. You get the option to add your coordinate system. What's the default one?
Yeah, I'll show you. Yep. So that this guy TCM element is actually correspond. Remember when we created TCM?
Mm-hmm.
It was defaulted to coordinate system local Earth and V and B axes. So that's why we're not selecting any coordinate system. Otherwise, if you create a user-defined coordinate system, you could select that there also. Yeah. So this is TCM element 2. I just populate these guys. I'm on figure 54, okay? So 1 e to the 0.05. Perturbation is 4 zeros minus 10 e to the 300. And max step is 0.002. And the key point here is, as I mentioned before, is this should be TCM dot element 2, which corresponds to the normal component. So hit apply, and we do the same thing with TCM dot B. And again, we change this guy to be TCM dot element 3. Click on edit. And make sure you select TCM actually here, because by default it references MOI. Double click on element 3, it brings it to the right hand side. Click OK. So I'm on figure 56. I'm essentially going to copy and paste all these values from there. Max partition is 0.002. TCM element 3 is selected. Click apply. Now apply TCM. So by default, in Burn, TCM is selected. If in this drop-down menu, you'll also see MOI, Mars Orbit Insertion, but we want TCM, and spacecraft is selected to be Maven, which is good. So we don't need to change anything here. Now we click on prop 280 days. The same story here, story goes here. The key point is that in the propagator, by default, GMAT references the first propagator that you create near Earth. We have to change this guy to deep space. And then we'll also change Mars elapsed seconds to elapsed days, and then we'll equate that to 280 days. So I click on this gray box, I select deep space. And I'm on figure 58 of the tutorial, okay? We're just essentially trying to make it make the figure look like this image. Change elapsed days to change elapsed seconds to elapsed days. Change it to 280. Let me just make sure I selected deep space. Yep. Now prop to Mars periapsis. Now again, by default, it's selected near Earth. We need to make this guy to be near Mars. And parameter will make this guy to be Mars periapsis in the parameter list. So I click on this gray box, I select near Mars, and the parameters I select periapsis first, and then we'll select the central body that it has to reference. So I select periapsis, and in the central bodies we have to make sure we select Mars. Bring it to the right hand side, Mars periapsis, and we're done. Just click on apply, okay. Now achieve b.t. Click on achieve b.t. by default the goal is Maven Earth RMAG. We'll convert that to Mars inertial dot b.t. Make it same as figure 60. So click on edit. You first go to b.t, and the main thing to select here is in the coordinate system, make sure you select Mars inertial. So I'll select Mars inertial. So now this should be maven.marsinertial.b.t, and we're making this value to be 0. And we'll make the tolerance to be relatively tight, 0.0001. Click OK. Now I go to the second constraint, which is b.r. Double click on it. Again, by default is maven.earth.rmag. We'll make it b.r, marsinertial.b.r. So I click on edit. We select b.r. Again, the key point is the coordinate system field here. You should select this to be Mars inertial. Mars inertial. And the value for this, remember, is minus 7,000. Because we want the asymptote of the incoming hyperbola to be piercing through at coordinate systems of coordinate points of 0 and minus 7,000 kilometers at the on the B plane. We'll make the tolerance to be very loose. Okay, so we're at this point. We're at the point where we can begin to run the mission. So I'll actually you just run the mission through this run button here. And if we did everything right, hopefully we'll be getting close to Mars periapsis after some iterations. And one thing, I'm not sure if Joel mentioned that all the iterations are shown in GMAT's message window on the bottom. So at this point, you're seeing all the perturbed iterations, all the iterations that it's leaving Earth view, and it's going to do that transfer arc in solar system view in the middle, and the Mars view. There you go. So the red trajectory is actually the final converge solution. So let me zoom in. So Earth view is actually the departure from Earth. And the solar system view, let me click on each one of them actually and make it bigger. So that's the outgoing hyperbola, the final converse solution. And the middle, let me first zoom out. So the transfer arc is shown in red, the Earth orbit is in green, and Mars is shown in yellow. Well, actually, it looks like it's orange. And the transfer trajectory is shown in red, and it's rendezvousing with Mars at this point. And the third view is Mars view. You'll see that it actually stops at Mars periapsis as a final converge solution. And in the message window, I'll show you the converge solution here actually. You'll see here that we had two constraints. The three variables that we were varying were TCM element 1, element 2, element 3. This is a converged solution. And the constraints we had b.t, desired was 0, and we achieved a relatively good accuracy that we gave. And b.r was minus 7,000, and we achieved it to a relatively to the accuracy that we want also. Let me zoom. And once again, the GMAT just gives you the final converged solution in this format, also in the message window. But I'll show you a second place where we can actually access these solutions also. Okay. So at this point, I'm on page 97. Okay, so if I click on apply TCM here, actually before I do that, let me click on target desired B-plane coordinate. And if I click on this button right here, apply corrections, what it's going to do is that the solution that it found in this TCM element 1, 2, and 3, it's going to put them in as initial guesses into TCM.V.N.B. So that next time when you run this targeter, it's going to converge in essentially one iteration. So we'll do that together. So I'll hit apply corrections, and you'll see in the bottom here, it says that apply corrections has changed the initial guess for TCM element 1, 2, and 3 to the converged solution. And we'll make sure that it indeed has done that. So if you click on TCM.V, you'll see that it has inserted in the converged solution. Same story with TCM.N, and same story with TCM.B. And the second thing that I wanted to show you is apply TCM. If you click on right click and go to command summary, this gives you a nice command summary of the maneuver. If you scroll all the way down, it tells you the delta V vector, the 3 components, and the magnitude delta V. It took around 7.24 meters per second, and the mass that was expended to achieve this the constraints was 6.31 kilograms, and the remaining mass that we have is 1711, because the original mass was 1718 actually. So this gives you a nice summary. I'll come out of it. And actually, just to make sure that we achieved the constraints that we want, I can click on achieve B.T, right click, command summary. And the key point here is that make sure the coordinate system is changed to Mars inertial, because we want to make sure that whether we achieved the constraint or not. So Mars inertial. You look into the hyperbolic parameters. B.T is minus 0, essentially 0 kilometers, and B.R is minus 7,000 kilometers. And the inclination that it results in is 90 degrees actually. That was our key point, that we wanted to hit this inclination, and the way you do that is by selecting the B.T and B.R on the fictitious B-plane that is attached to the central body Mars. And again, you do the same thing, B.R, you'll see that make sure you select the coordinate system to be Mars inertial. In the spherical hyperbolic parameters, you'll see that B.R is minus 7,000. And the resultant inclination is 90 degrees with respect to Mars inertial. So if I run this mission again, it should converge in maybe one iteration, because we've already inserted in the final solution as our initial guess. Should take maybe 1 or 2 iterations. Actually, let me stop that. Let me minimize this. Let me run this again. There we go. 1 iteration, and you're just getting a converged solution. So now, at this point, since we're at close to Mars periapsis, we'll go ahead and create a second targeter. Okay, that will actually help us capture about Mars. So we're actually on page 98. And this is just a screenshots of the converged solution during the first targeting sequence. And the second targeting sequence will create this second targeting sequence, in which we're going to name it Mars capture. And this time we'll only insert one control variable, which is MOI Mars orbit insertion.v. We'll vary this guy, and we'll apply the MOI. We'll prop to Mars apoapsis, and we'll make sure that we achieve an RMAG of maybe 12,000 kilometers. So that's our constraint, and that's our control. So it's a 1-by-1 targeting sequence. And then once we're captured, we'll actually propagate for 1 more day so that we can actually see the entire captured orbit. Okay, so we just click on, I'm going back to GMAT. If you click on mission sequence, now I'm following instructions which are these instructions right here, okay? These instructions here, right below figure 65. So I click on mission sequence, append, I do target. It's gonna create a second target sequence right below the place where the first targeting sequence target sequence ends. I'll rename that to Mars, just like before. Rename that to Mars capture. And now we'll begin to append all the commands. So I click on right-click append. We append vary. You rename that vary to vary moi.v. So first we're just creating all the commands, and later on we'll go in each command and we'll manipulate them as what we want them to do. Append, you append a propagate. You rename that to, I'm sorry, you actually append a maneuver. So I should delete this, because after vary you need to apply the maneuver. Apply maneuver. Rename that to apply MOI. And after that you append a propagate command. You rename that to prop to Mars apoapsis. And then we append an achieve command, rename that to achieve RMAG. And then so we should have vary MOI dot v, apply MOI, prop to Mars apoapsis, achieve RMAG. And according to figure 65, we'll also insert in prop for 1 day. So we can just click on, you can click on this guy and Mars capture, right click, and you can actually just say insert after, and you'll just do propagate. Rename that to prop for 1 day. Now we'll go in each sequence and we'll actually each command will actually vary them all, okay? Before we do that, we should click on the second target sequence, Mars capture, actually, and make sure we select the exit mode to be I think what's it called, save and continue. And again, the reason we're doing that is because after each target iteration, it's gonna pick up on that first initial guess and then make it as a, apply that as an initial condition during the second targeting sequence, second targeting run. Vary MOI. Now this is a key step here. So at this point we have to make this guy MOI instead of the default TCM. So we click on edit, select MOI, element 1, it brings it to the right hand side, okay. And we begin to just populate these values for initial value, perturbation, lower and upper and max step as shown in figure 69. So initial value will give it minus 1.0 kilometers per second, perturbation of 0.00001. Lower value will make it really big so that the solution space is quite large, and upper value will make it similarly very big. And perturbation will just max step we'll just do is 0.1. Click apply. Now apply MOI. We select MOI, and the default is TCM. Good. Okay. Select MOI. Spacecraft is Maven is fine. Next, we click on Prop to Mars Apoapsis. Now again, the default is near Earth. We need to make that to be near Mars, because Mars gravity is the primary force that is governing the trajectory. So Mars, near Mars. And in this guy parameter, we need to select that to be Mars Apoapsis. This guy. Select this guy to be Apoapsis. The key point here is, again, we need to select central body to be Mars, okay? But default is Earth. So in the drop down menu, just select Mars. Just click on this arrow right here. It's going to bring it to the right hand side. So it's going to be Mars Maven.Apoapsis. Near Mars is the propagator, which is what we want. Okay, achieve our mag, our constraint. So by default, it's a reference to Earth, the RMAG. So we'll just reference it to Mars. So it's going to be Mars, maven.mars.rmag. So we click on this edit. So first you go and look for RMAG, and then you reference it to Mars. RMAG, central body to be Mars. Bring it to the right hand side. Okay. And the value that we want the differential corrector to achieve is 12,000 for now. And tolerance, we'll just leave it as 0.01. As 0.01. Now at this point, I'll just go ahead and actually amend the last segment also. So in here, we again select near Mars, and we make this guy to be prop for 1 day. Now elapsed seconds, I can just make it to be 86,400, which is same as 1 day. Instead of changing it to elapsed days equals to 1. I'll hit apply. Now I'll run the sequence. At this point, we're ready to run. Again, we run the sequence by clicking on this run button. If we did everything correctly, then I think we should capture about Mars into a relatively decent sized elliptical orbit. And I can't see my third window, which is bad. It's hiding somewhere, but it's okay. We'll just rerun it. See, during each iteration, it was trying to make. There you go. So we've captured, and these two figures are actually this was the outgoing hyperbola that we saw before. Nothing unusual about this, and the transfer trajectory shown in red that the first targeting sequence achieved. But the key point is the second capture orbit about Mars. So it stopped at Mars periapsis. It did a burn against the incoming hyperbolic velocity vector, and it captured about Mars. So let's see if it actually will do the same thing as before. We'll actually hit apply corrections so that it can take the final converge solution and put it into the targeting sequence.
Where do you pick up that button? Like,
I'm sorry, okay, so if you click on Mars capture
right,
and
like, right.
exactly, yeah, just click on that button. And you should see in the message window that apply corrections has changed initial guess for MOI element 1 to from -1.0 to the final converge solution. And you can make sure of that by clicking on vary MOI.v, and you'll see that the final converge solution is the initial value is the final converge solution that the second targeter came up with. And we can do the same thing here again. I can just click on apply MOI and see how much delta V it took by accessing the command summary. Again, the impulsive burn is MOI, VNB is the axis, delta V vector is burn only in the velocity direction, in this case minus. And then that's the magnitude, and the amount of fuel that it took was 1076 kilograms. It's okay, I'll show you again, don't worry. So you come to Mars capture, the second targeting sequence, and you right click on Mars MOI,
Right.
and you'll see a command summary. You'll see this guy.
Oh, I see.
And you click on this.
That's what it was.
Yep. I'll just go there again. So the remaining fuel that we have actually in the tank is 635.62 kilograms, and the amount of fuel that it took for the second burn was 1076 kilograms. And we can actually go ahead do the same thing in our constraint command. Achieve RMAG, right click, see if we indeed achieved RMAG of 12,000 kilometers. Right click, command summary. The key part here is actually change this guy to Mars inertial, because you want to see with respect to Mars inertial coordinate system. And you'll see that RMAG is actually 12,000 kilometers. And we still have the inclination of 90 degrees for the final capture orbit. And the reason why it's obviously changing is because we have a non-spherical gravity around Mars, so it's perturbing the inclination. If we had a point mass, it will be dead on 90 degrees. Because even within, I think, 12 for 1 day, it perturbed the inclination by some decimal place. And one cool feature that we just added in, I can just quickly show you, is actually instead of changing, oh my bad, I had to close this guy. I can quickly show you, instead of Mars ellipse 11 seconds, we'll just stop that to be Mars periapsis. I just want to demonstrate to you the colors capability that we entered in GMAT. So Mars, we'll just make that yellow. So the default colors in GMAT are always red. You can now select colors for each propagate command, and you can make it whatever you desire. There you go. So it first propagated to the apoapsis and achieved 12,000 kilometers, and then it from apoapsis it returned propagated back to Mars periapsis. So you can now assign different colors in GMAT also to each different propagate command. I think this is it. Any questions? Comments? Okay, so my turn is up. Next is Steve Cooley. He's a senior flight dynamics engineer in our branch. He was actually the mission design lead for LCROSS mission, so if you have any questions about LCROSS, feel free to bug him. Okay, let me...
So is this the